All right, I ask you to think about this problem, and we did a couple of first steps to actually solving it. So the first step we did is to just draw the forces which act on this charge. This is the force F1. It's the force due to the charge number 1, so this one, and the force F2. So charge number 1 and charge number 3 repel each other, and this is defines the direction of the force F1. The charge number 3 and number 2 attract each other because they're opposite, right? So it will be in this direction, like this, and we found the net force. So approximately it will be like that. Okay, it's quite approximate though. So what we are going to do now, we're actually going to solve this numerically and see the direction of the force. Okay, so to solve it numerically, we'll follow the following rough plan. Okay, so the first step will be to find the magnitude of both forces F1 and F2. Okay, that's the first step. The second step is to find the vectorial representation for both forces. So vector F1 and vector F2. Okay, so this is F2, F1. Okay, the next part will be to find the net force, which will be given F net by the vectorial sum of F1 plus F2. And we will find it as well. Okay, and finally the fourth part will be is to find the polar representation, polar form for F1. Okay, so for that we would have to find this angle over here. It's the angle from the negative x-axis theta and the magnitude of this form. And the magnitude of this force, F net. Okay, so let's proceed with this plan. We will start with step number 1 to find the absolute value of F1 and F2. I will clean it up a little bit here. Okay, so F1, to find its absolute value, we'll use the Coulomb's law, which tells us that it's given by the Coulomb constant times the magnitude of the vector q1 times the magnitude of the vector q3 divided by the distance between them. So let me call it squared. Let me call it distance d13 squared. Okay, so now let's substitute the numbers. Okay, so we know what k is. It is 8.99 times 10 to the positive 9 Newton times meter squared divided by Coulomb squared times. Okay, so now we have the product of the charges. Each charge here expressed through E, right, through the elementary charge. So we have Q1, which is 2E, okay, multiplied by Q3, which is 2E. Okay, very good. So it will give me 4e squared. Okay, so let me just write this in the following way. So it is 4e squared. Okay, we also know what e is, right? So instead of e, I will have to substitute 1.6 times 10 to the negative 19 coulomb. Okay. So now this is divided by the distance between them. The distance is 2 millimeters. We have to use SI units. And this is 2 times 10 to the negative 3 meters squared. Now we will use our calculators to compute all of this. So by the way, so 1.6 is the electric charge, so this is E, so to be clear. So when you are substituting this into this equation, you have to square it. Okay, so substituting the numbers and computing the result, we will obtain 2.3 times 10 to the negative 22 Newton. And you can check that it's actually Newtons. You will see that meter squared cancel out in this equation, Coulomb squared cancel out in this equation, and the only unit you will end up with is Newton. So the same algebra we do for the force F2. The only difference here is that we need to use a different distance. and we need to use different charge Q2, okay, Q3, Q3, and the distance is distance between 2 and 3 squared, and after this we substitute the numbers. Okay, the distance here is 4 millimeters. We shouldn't forget about this. We need to convert it into SI units, into meters. Other than that, it's all straightforward to do. Okay, we will obtain the following result. After using our calculators, it will be 5.75 times 10 to the negative 23 Newton. Okay, we found the absolute values of these two forces. Now what we need to find? What we need to find is the vectorial representation. Okay, we need to find vector F1 and F2. So let's start with F1. And for F1, we'll want to find the x component and the y component. So the x component, first of all, I would like to ask the following question, if it's positive or negative. But for that, let me redraw this figure. So I have the x-axis, the y-axis, and so this is my vector F1 approximately. So I know that this angle from this graph is 30 degrees. Okay, it's written over here in the picture over here. So that's why this angle is also 30 degrees. Okay, that's as useful information. I know the absolute value of this vector F1 given by this side over here. Okay, I need to find the x component of this vector. Okay, the x component F1x, and I need to find the y component of this vector F1y. Okay, F1x. So the first question I always want to ask if it's positive or negative. And from the picture, you can see that it is in direction opposite to the x-axis, right? And therefore it's negative. And this is why the picture always helps you to solve the problem, right? So just by drawing this figure, you'll be able to, you will be able to see that this is a negative number for the x component of this force. So minus sign times what? Okay, it times the magnitude of this vector F1x, F1. And now I need to find if it is a cosine of this angle 30 degrees or sine of this angle 30 degrees. Well, in this case, it's cosine. Why is it cosine? Because this is hypotenuse and this is the adjacent angle. And therefore, I use cosine of 30 degrees. I substitute the numbers to obtain the result here. It will be minus 1.99 times 10 to the negative 22, 10 to the negative 22 newtons. Okay, what about the component y? Well, the component y is also will be negative. You can see it from this picture. Very good. Next, I have the force over here. It's absolute value, which we already found, times sine of 30 degrees. Well, we used already cosine, so I don't think it can be now it's sine. But you can also see that this side, well, which corresponds with this side, is opposite to the angle of 30 degrees, and this is why it's sine. Okay, doing this simple calculation, sine of 30 degrees is actually 1/2. So the only thing we need to do is to take this number and divide by 2. Okay, take this number, divide by 2. We'll obtain 1. And don't forget the negative sign. 1.15 times 10 to the negative 22 newtons. Perfect. So we found the vectorial component for the force F1. So actually, let's write it as a vector. So F1 is minus 1.99 times 10 to the negative 22, comma, and the y component is minus 1.15 times 10 to the negative 22. Okay, and these are all newtons. Perfect. We will highlight this result because we're going to use it in the future. Okay, and continue with calculations for the vector F2. Okay, the vector F2 actually we can find easily. Okay, it's just because, I mean, from this figure it's kind of clear. It only has non-zero x component, and therefore its magnitude is the same as the x component, and it is positive, right? It's positive because it's in the direction of this vector points in the direction of the x-axis. Its magnitude just its x component, nothing else. So it is 5.75 times 10 to the negative 23, okay, comma. Well, what about y component? It's just 0, right? So it's 0 newtons. Okay, perfect. So now we have these two vectors. What we need to find is the net, okay, vector. Well, for this, we need to add these vectors together. How do we add the vectors together? We add x components together, and separately we get y components together. Okay, so what we're going to do, we're essentially just going to add. We will add these two numbers and these two numbers and write, the answers. Okay, adding these two numbers, so the x component first, so adding these two numbers, we will obtain minus 1.42 times 10 to the negative 22. Okay, that's it. So adding these two vectors or adding these two numbers, and it's pretty straightforward. We'll just rewrite this minus 1.15 times 10 to the negative 22 newtons. So that's our result for the vectorial form of the net force. And by the way, we can see that both of these components are negative. So let's actually draw this net force again. Just to clean up the figures. So this is y, this is x, both components are negative. It means that it has something, it looks something like this. And what we need to find now the polar representation for this force. In other words, we need to find this angle theta, and we need to find this magnitude of this vector f net. Okay, I mean, how do we find a magnitude of any vector, as a matter of fact? So the magnitude of any vector, okay, so this vector with components ax and ay, how to find its magnitude? Okay, how to find its magnitude? It will be square root of ax squared plus ay squared, okay? So this is pretty straightforward algebra. We have to perform to find the absolute value of the vector. So, well, here we will use the vector f net to do the same type of algebra. Okay, so the absolute value of f net, okay, will be given by square root, okay, of the x component squared is minus 1.42 times 10 to the negative 22 squared. When I square the negative number, it will become positive number. So this minus doesn't really do anything here, right? So plus now there will be y component is minus 1.15 times 10 to the negative 22 squared. Again, so this minus sign over here doesn't really play any role, because once I square it, it will go away. Okay, so and the result will be in newtons. So doing this calculation, squaring, adding, and then taking the square root, I will obtain 1.83, okay, times 10 to the negative 22 newtons. Next, I need to determine this angle theta. Okay, so I actually can use the following definition of tangent. Let me remind you that the tangent of the angle is given by the ratio of the opposite side divided by adjacent side in the corresponding triangle. Okay, so let me draw this triangle over here. Okay, so let me draw this triangle over here. So I need to find, I need to find this side. Well, I actually know this because it will be given by the absolute value of f net y, right? So this length is the same as this number, right, without the minus sign, because it's length can be negative. So this length over here is the same as this number without negative sign again, because the length also can be negative. And tangent of this angle theta will be given by this length divided by that length. Okay, so this length is f net y, and this length is f net x, and again, this is just absolute values. So tangent of theta is given by f net y divided by absolute value f net x absolute value. Okay, this is tangent. What we need to actually find is theta, but we know how to invert tangent. We need to find arctangent. Oftentimes it is denoted by this tangent minus first, but tangent minus first means just inverse function, though it's arctangent. Okay, it's arctangent of what? Of f net y absolute value divided by f net x absolute value. Perfect. So now we can substitute the numbers. Tangent, arctangent, okay, of the following. So I have f net y. So it is 1 point, and its absolute value 1.5 times 10 to the negative 22, but they will cancel, as you can see, in denominator and numerator, so I will not even write them. So, and so the net x is 1.42 from this, right? Okay, 10 to the negative 22 in numerator and denominator will cancel out, so I'm not going to write them. So finding the arctangent of this ratio, using my calculator, I obtained 39 degrees. When we write the angle, we have to specify in what direction it's counted, and in this case it was counterclockwise, okay, from negative x-axis. Okay, so that's this angle over here, counterclockwise from negative x-axis. Okay, so this is our answer now. Let's highlight it over here. So we found the net force, its magnitude, and we found its direction. Okay, too much highlighting over here, so let me remove this, and its direction. Okay, and that's the answer.